So one of the foundational ideas in physics, we have Newton's three laws of motion. This idea of inertia. Okay, so those are Newton's three laws. It's actually the law of inertia is Galileo's three laws of inertia. But you have those. You have inertia. You have the discussion of forces producing acceleration, the second law, and then the equal and opposites. Foundational. Okay. You have the idea of conservation of energy. This idea, if it's almost it's almost a, a big idea, in that if you look at the entire universe and you forget about what goes on in the realms of nuclear physics, um, that whatever amount of go juice that you have in the beginning is the exact same amount of go juice that you have at the end. A big, big idea. Okay? And it doesn't seem like a big idea. It's just because you're not looking at it in a big system. Okay? If you imagine that if right after the Big Bang, I won't talk about the Big Bang, if you had a device that was able to measure all of the energy of those objects that are moving and all the thermal properties and all the gravitational energy, all that stuff that's being released at that Big Bang, if you could measure that, it would be the exact same number that we would have now. It just would be be almost impossible. Well, it would be impossible to measure all that energy. So it's another really, really big idea. The third big idea, and in my personal opinion, I think this conservation of momentum is far more important than the conservation of energy. In that, it's always true. Um, we find out later when we talk about nuclear physics that energy isn't always conserved. We find out in collisions in momentum that um, inelastic collisions are not conserved energy collisions. That you can't presume that all the energy in the beginning is equal to all the energy at the end. Now that's not necessarily true. You're just not broadening your view enough. But how broad do you have to make your view to talk about a car crash? I mean, really. So conservation of momentum is one of those really big ideas, and it's a really important idea. And it's a really simple idea. All conservation of momentum says is that the initial momentum, which is p, I don't know why it's so. One of these days I'll do enough research to determine why momentum begins with a p. The initial momentum is equal to the final momentum. It's that principle, okay? So, and that's too simplified. If you will, it's the initial momentum of the system. It's everything that you've observed. It's not like I have to go back to the Big Bang and observe all the events that happen up there in order for this law to work. Instead, what I have to do is I've got to look at pre-collision, post-collision. I look at the motion of all the objects in the beginning of it, the motion of all the objects at the end of it, and I do a little bit of math, and those numbers should end up equaling each other. They have to, regardless of the type of collision it is. Okay? So the initial momentum, if you will, is the momentum of every object in that system. On and on and on and on and on. Is equal to the momentum of all the objects in the system after an event. Okay? So, in the case of a car collision, this is the two cars moving, and this is the innocent bystander standing on the side of the road. Okay? And there's the cop car that's involved, and the bicyclist. All of those objects, if you look at them initially, all of their momentums. Okay? Now, all of those objects have to be involved in that collision. After it's done, whatever number that is, whatever you calculate it to be, that should be equal here. So in the case of a car collision, if they all come slamming together, and there's 5 cars in that collision that all kind of intersect at one point, I have all those momentum. They all come to a crash in the middle, and they all stick together, and I just left with one momentum. So that number that you're left with has to equal that number there. Let's talk about on the atomic scale. If I have proton, neutron, proton, neutron, proton, neutron, proton, neutron, I got a couple of alpha particles slamming into each other. Okay, and they all bond together. All of their momentum initially has to equal that one momentum final. Take it the other way. In case of an explosion, so I've got myself a bomb. Okay, it goes off. I gather up all the information I have. Its initial momentum, whatever that may be, is equal to the momentum of every single piece of that bomb after the explosion. Okay? That's all that means. Okay? Whatever I start off with is whatever I end up with, regardless of what's going on. Now, there are some systems we claim that the momentum is not conserved. The object of throwing a ball up and catching it. Well, the ball had no momentum. You throw it up. My hand actually is gaining positive momentum. The ball is gaining positive momentum. It looks like it's a violation. Much like energy, you just haven't taken your system to be big enough. Those objects may be gaining momentum, but something else is gaining negative momentum. That's the Earth. They're pushing it down. It's moving down. But because the Earth is so massive compared to the ball, so little momentum is being created when considering the entire mass of the Earth, we just tend to ignore it. But that's the principle. That is conservation of momentum. And it is the big idea. Okay? The three, you got Newton's laws, conservation of energy, conservation of momentum. Those are huge, huge, important rules. And in my opinion, well, next to Newton's 3 laws of motion, conservation of momentum is probably one of the more important.